Let's introduce some further terminology, and one piece of terminology that's relevant for this chapter is a map. Now, you all know what a map is in daily life. However, in this chapter, a map is something completely different. A map is actually a function, and not just any function, but a function where the input space is the same as the output space. So the input space is the same as the output space. Why is this relevant for our context? Well, if you have a certain output that you get out of your map, since the output space is the same as the input space, this means you can feed back the output to the input of a next iteration. And that way it's possible to construct a discrete time dynamical system. So you need an update rule that's a map for that. So you can construct things like f of x, right? Or even f of x. But since this is so complicated to write, we have a shortcut that we define like this, which so we're going to write f2 of x, basically means applying f twice. Now, obviously, outside of this chapter, if you were to see f2 of x, you might think that this is equal to f of x squared. But in this chapter, that's not the case. This is just out of laziness that we introduce this shortcut here to write down successive applications of our map. Okay, let's bring in some new terminology, even more. So if we have a certain initial condition x0, then we can keep on iterating. We can start from x0, and then we have f of x0, and then we have f2 of x0, and so on and so forth. So the collection of all of the points that are visited, starting from an initial condition x0, this is called the orbit of that initial point x0. And of course, the ultimate fate of an orbit is something very relevant to know in practice. So for example, it's very obvious to see that for the case of the very simple growth model that we had, where f of x was 2 times of x, the number of bacteria will basically grow towards infinity, right? So this is an unstable system that will explode, and therefore it's not a very realistic system, because in a realistic system, as the population increases, you might imagine that there's more and more competition going on for a limited set of resources. So therefore, what happened initially with the growth factor of 2 might have smaller growth factor as the population increases. So let's also see if we can model this type of more realistic growth. And in order to do that, we're first going to do some rescaling. So let's say originally our population came from the set of integers, right? And let's say that there's some sort of maximum number of population that we tend to study. And we're going to rescale that to a collection of numbers in the interval 0 to 1. So this, where 1 is some sort of maximum reference value. So in this case, we went from a discrete set of states to a continuous set of states, because these are just continuous real numbers. But bear in mind, this is still a discrete time dynamical system, because we keep on iterating. We only look at our Petri dish, for example, once every hour. Okay. So if we rescale this, we can think of making our model more accurate. And the way we want to make our model more accurate is by looking at this growth factor here, which is 2 in this original case, regardless of the value of our population x. What we now want to do is we want to tweak this growth factor a little bit such that it depends on x, in the sense that initially for small values of x, it's still close to 2. But then as x starts to increase and then increase towards this maximum value of x equal to 1, then this growth factor should peter out. So pause the video and see if you can imagine an equation that would capture the behavior that I've just described. So if you replace this 2 in this equation by 2 times 1 minus x, then we see what happens here is what we want. Because if x is small, so let's say it's pretty close to 0, then in this case our growth factor is still 2, as it was originally. But then you see that if x increases, and it increases towards our maximum value of 1, then we start to multiply this number 2 with an ever smaller value until in the limit this growth factor becomes 0. So the population doesn't grow anymore. So this means that our update rule now looks like this. It's f of x 2 times 1 minus x times x, where this thing here is our growth factor, or we can interpret this as our growth factor. This is a very famous model for growth. It's called the logistic growth model. And you might wonder in this case, what will happen to our limiting state? It's no longer going to go towards infinity, as in the very simple case of linear growth. What will happen here for this logistic growth model, which is a non-linear model because you have x times x here. But then you can just write a simple computer program, or if you're old-fashioned, use a calculator or whatever. And then you see that if you start from a small population, that eventually the limit here will end up at the population value of 0.5. So it no longer has boundless growth. So that's more realistic in this case. What we will do next is see if we can have some sort of graphical construction that will help us verify indeed that the limiting population for this logistic growth is indeed 0.5, but that's for the next video.